This conference will now be recorded.
Hello. Welcome participants to the second session of day one. This session will be conducted by Dr. Manohar Singh, who received his BE degree in electrical engineering from the Government College of Engineering and Technology, Jammu in 2003. He did his MTech degree in electrical engineering power systems from the IIT Roorkee in 2010 and PhD degree in again electrical engineering from IIT Delhi in 15. Presently, he is working as an engineering officer in the Power System Division of CPRI, Bangalore, India. At CPRI, he is extensively involved in applied research and consultancy in power sector. His research interests include power system protection, power system simulation and modeling, microgrid, grid operation and control with bulk penetration of renewables. He has published around 35 research papers in international, national journals and conferences, worked as a consultant on various industrial, government power utility and conducted training, uh, workshops, tutorials for power utilities like Makra Bees Management Board and in Center of Collaboration Advanced Research, CCAR, CPRI. He is also a senior member of IEEE and IEEE PES member and executive member of IEEE PES Bangalore chapter since 2006. He is also a member in the board of studies of Visvesvaraya Technical University, Belgavi and Government Engineering College, Jammu. He is a regular attendee for the top international IEEE PES conference across various parts of the world. His research work based on cluster-based protection coordination using a new voltage current time inverse relay has been awarded as one of the best research power during PES General Meeting 2018 at Portland, USA. So now I would request Dr. Manohar to start the session. Please, sir.
Hello, yeah, good afternoon to one and all. Thank you, Dr. Sanjay Agrawal, for introducing me to the this meeting attendees. Really, it's my pleasure to interact with all of you. I hope my voice is clear. Dr. Sanjay, you can confirm me.
Yes, sir. Your voice is clear.
Thank you.
Yes, your voice is clear.
Thank you very much. Yeah. So the title assigned to me is the National Grid Operation, Operational Emerging. Oh yeah, issue is I have not typed there properly with a high penetration of renewable. So this is around I think 90 minutes are given to me, and I will try to complete my presentation within 80 minutes and wish to spare the 10 minutes at the end of presentation towards the queries which I get from you people. In between, if you feel that somewhere you can interrupt me for queries, you can type me your queries through the chat box, or you can directly speak to me if you have the control to speak. Uh, dear friends, as we know that the grid operation is a very complicated issue. Typically, when the size of the grid is very big, and of course the grid is a very vast network, and it involves, I should say, thousands of kilometers of transmission lines. And typically in India, we have the transmission lines of 765 kV, plus minus 500 kV, and 400 kV as a major backbone of the transmissions, and we have 220 kV also and 132 kV. Mostly those are under the jurisdiction of the state transmission companies. But coming to the main grid, as I told, 765 kV and 400 kV lines are there, and the DC HVDC plus minus 500 kV lines are there. Why we require this huge infrastructure? This is a very fundamental question. Majority of you are quite aware that, just I'm looking for one second slide moment. It's not good. Yeah. I wish to speak for around 10 minutes on the basis of the fundamental of the grid operations. Then we will switch over to what will be the emerging issues, especially with the high penetration of renewable will get in the future. So as I told, though it's a very vast network of thousands of kilometers of transmission lines, and why we require this such a vast grid? What happens nowadays, still I should say, the majority of generation we are getting from the centralized power plants, and those are located at close to the raw material. Typically, if to coming to the Indian context, we have around, I should say, 65 to 70% of power generation coming from the thermal powerhouses, and those powerhouses are located in the central portion of the country. Then we have some hydro potential that is localized on the Himalayan states, and unfortunately, we don't have the load in the Himalayan states or the central part of the country. The majority of the load is located on the western part of the country and the southern part of the country and other metro cities what we have. So what I mean to say, wherever I have the generation, load is not there. Load is away from it, maybe 1,000 kilometers and sometimes maybe around 2,500 kilometers. And that's why we have very long transmission line corridors of 2,000 kilometers, and somewhere the length is around to 3,000 kilometers. Like Northeast line is coming to Delhi, that is around 3,000 kilometers in the length. Such a vast network is there. So in order to transfer the power over such a long distance, we require this high voltage transmission line corridors. So this is the essential need. But okay, that's a different issue. But point is there, from the grid operation point of the view, what are the issues today we are facing with the conventional generations? Just leave the renewable with the conventional generations, and what is the scope of that organization which takes care of the grid operations? Dear friend, we know that power grid is there. The main aim of the power grid is to make the power infrastructure only, just to make the new power corridors wherever the power generation is coming and wherever the new load centers are coming. Their role is not to float the power on the network. Their role is confined to develop the power infrastructure. But there is a separate one organization known as a POSOCO. So their role is to route the particular amount of the power on a particular transmission line at a particular time. So as a grid operator, actually they are the grid operator, that POSCO, Power System Operation Company, they are the grid operator. So their aim is to, depending upon the load requirement in a certain pocket of the country, route the power to meet the load requirement. Okay, so how they will route it? So routing, actually it involves many factors. It is not only, I should say the technical constraints are there. There are some economical constraints. So they have to route the power in such a way where the cost routing is minimum. But I am not going to discuss here the power economics and all those issues. But I wish to confine myself to the technical constraints what as an operator they face. So directly see, as I told, it's a very vast networks, and typically the operation is not, I should say, centralized. The operation is a highly distributed in the nature. Actually, that slide I have here, yeah, you can see. Operation is totally distributed in the nature. We have the centralized controller sitting in the Delhi, known as the National Load Dispatch Center (NLDC). This NLDC, and then whole country, since it's a very vast network, the whole country is clustered into different regions. Like you people are in the northern regions, and now presently I'm speaking from the Bangalore. I am under the southern regions, and similarly there's a western region, eastern region, and the northeastern region of the country. And like you people, as I told, you are under the northern regions. You have your head office somewhere in the Delhi, and further, whatever the total, there may be 5 to 6 states in the northern regions. Those are controlled from their individual load dispatch center. You have your own load dispatch center in the Lucknow. Okay, so whatever the total load in your UP state, or whatever the generation you have in your UP state, that is regulated, or I should say controlled by the state load dispatch center. So this, okay, that's a different thing. What I told is a mechanism how it works. But as a operator, as a grid operator, what technical things I have to keep in my mind? So there are two fundamental things. One is the voltage. So all times I have to assure that voltage remains stable in the network. I'm sorry, just there's a call. I will speak for 20 seconds to them. Otherwise, they will keep understanding. Hello. गुड आफ्टरनून सर जी. सो सर हमारा प्रोग्राम 21 ऑनवर्ड्स है, हम उस पर काम कर रहे हैं, एंड विल शेयर द लिंक. हाँ कर रहे हैं सर. ओके. और हमारे सर आई थिंक आपको बिल सर आगे होंगे पढ़ाने वाले दोनों. पहले ग्रुप 1 और ग्रुप 2 के. हाँ भेज दिए. विश्वास को. ओके, थैंक यू. Yeah, so I'm back here. So as an operator, he has to ensure the total generation and the total load if I assume the loss in the system is zero, so whatever the total generation he has in the hand, that much he has to meet the load in the country. So net power in the grid should be zero. I, so when the total generation and the total load are matching to each other, so at that time what happens? The frequency of the system remains stable. So as an operator, he will always see the frequency. But of course, it's very challenging to manage the total generation, the total load in such a vast network. What happens? Definitely, there will be some mismatch. That mismatch may be 2% or 3%, or no, 2% still is a very big figure. It may be close to less than 1%. So that may cause some fluctuation in the frequency. That is why, as per the Indian Electricity Grid Code, some window is given to the operator. If the frequency is fluctuating within that small window, that window is nowadays too stringent. It is only plus minus half hertz. I have wrote here at the bottom of the table, you can see it. If the fluctuation in the frequency only plus minus half hertz, still he can operate the grid. There is no penalty on the grid operator. Okay, so this is one requirement. It is not only the voltage. There's another requirement that's free. Yeah, it is not only the frequency. There's another requirement, that's the voltage. So in order to manage the flat voltage in the system, flat means 1 per unit everywhere. If it is saying 765 kV station, he has to maintain the 765. If it's a 220, he has to maintain the 220, whatever. So in order to maintain the flat voltage profile, he has to manage whole reactive power management in the system. Okay, as we know that our network is very vast. Majority of the lines, they are the inductive in the nature. They will consume the reactive power. Of course, in between there are thousands of the substations. At the substation, I have mostly transformer, and transformer is also that inductive in the nature. It will also consume the inductive power. So from where you will get that inductive support? So as an operator, he has to ensure that much reactive power generation in the system, and typically, fortunately, we have presently the synchronous machine there, which will give you sufficient reactive power support. So if he is able to manage active power balance in the system as well as the reactive power balance in the system, the frequency and the voltage remain stable within the allowable tolerances. For voltage control, I have a plus minus 5 that percentage voltage variation. If anything goes outside that allowed tolerance, then the operator will be penalized, of course. That is also there, and he will be simply penalized. So as an operator, all time he has to ensure the voltage and the frequency to remain within the window what I have listed in these slides. This is the main concern of the as an operator. Now, what is happening? See, as when I opened my presentation, as I told, majority of power we are generating from the fossil fuel, around 65 to 70%, and the remaining power comes from the hydro potentials or from thermal potentials. But fortunately, whether it's a thermal power plant, nuclear power plant, or this hydro power plants, ultimately they have machine whatever is there, that is a synchronous machine. And the capacity of that machine typically varies from 50 megawatt to now 660 megawatt. Such a big machine is there, and though size is something different, but the characteristic of that machine is a synchronous machine. And synchronous machine has a very high inertia, and moreover, it will give a classical frequency control feature as well as the voltage control feature. Many of you may be aware that frequency is controlled through its the droop characteristic. Okay, they have the governor there. So as per the regulations, if the rating of the machine is more than 50 MVA, that must be equipped with the governor. Okay, so if any small fluctuations which are coming from the load side, that can be simply offset with the help of the governor, that primary and the secondary control of the those synchronous machines. If any fluctuations we are getting on the voltage side, that can also be offset with the help of the classical control given to the synchronous machine from its exciter control. Okay, exciter is there. So this is the advantage I have with the synchronous machine. That is why in spite of large I should say reasonable fluctuation in the load in the country, the operator is able to maintain the frequency and the voltage control well within the desired limits, since he has the synchronous machine available at the most of the power generating plant, whether hydrothermal or the nuclear. But what is happening, unfortunately, I should say, from one context of the view, I'm telling unfortunately as an operator, but of course that we have to do. It's not, that is a very, I should say, very, it is a lot of advantages to produce the power from the alternate sources. So actually, there are the two fundamental drivers which are driving us to move towards the variable renewable energy generations. As most of you are aware, one is the emission of the carbon, this greenhouse gases from the thermal power plants. If we'll continue to generate our power from these thermal power plants, by the end of the century, our Earth, the temperature will rise to 3.2 to 5.4. So that will make our Earth unfit to live. So definitely we have to cut the greenhouse gas emission with a very sharp rate. In order to curtail the temperature within the 2.3 degree, so we have to generate our future energy demands from the renewable. So it is there. And second, in that huge development in the technology in the last 1 decade has resulted in the remarkable reduction in the per unit cost of generation of the electricity from the PV system and the wind-based system. And nowadays, if you see that the cost of the generation of the one per unit power from the PV or the wind-based system is as equivalent or even cheaper than the from a thermal power plant at this certain point. So this is happening. Just a minute. Hello. हाँ मैडम, आज नहीं मैडम अवेलेबल हूँ, इसमें मैं लीव पर हूँ, जिस कुछ भी चाहिए। Yeah, so I'm sorry once again, internal call was here. So actually these are the two fundamental key drivers which are forcing us to generate the power from the this renewable based system. So the trend is more or less, I should say, the uniform throughout the globe. Coming to the first just that international context, what I should say, where the countries which are quite developed and they have not that sharp increase in their load, annual increase in their load, like in the US, we don't see very sharp increase in the load. So that's why they don't have a much more incremental generation requirement. But unfortunately, now their power plants are quite old, like they're 30 or 40-year old. So what they are doing, they are trying to meet their retiring power generation with the help of the renewable based systems. Okay, since their demand is not increasing, then they don't require the new that incoming that generations, but their old generation is retiring. So what they are doing, they are trying to make their retiring generation with the help of the renewable based system. That is why you will see there is a renewable push, but conventional power is going down across the year. I think this slide is given from 2016 onwards. Yeah, 2002 to 2016. Okay, but countries like us or other developing countries where incremental load growth is there, and accordingly we have to meet the generations. So we are not retiring our power plants since our power plants are not so old like that 30 or 40-year old, but we are trying to make up our additional load requirement from the renewable based system. So keeping in all those things into mind together, how our future grid will look up. You will see on the left side, I have the conventional grid, where in that case you have the large synchronous machine, and typically we have the load what today we have. But in the future power systems, you will see a majority of generation will be coming from the green resources like PV and the wind, and the load what today we have, I see there will be also a dramatic change in the loading side, and mostly we may have a power electronics type of the load, and essentially we are looking for some new loads also in the futures. Like already we have now we can see that electric vehicle is one area, transport sector, where we will see reasonable amount of the loading will be there, and the nature of that load is totally different what the load today we have. So this type of the future system we are expecting. Since this will be a highly decentralized system, because smaller generating units will be there, their number may be in thousands, and the other side load will be also highly decentralized. So it will be very complicated to control the system. So what the advantage I have with the conventional system with the large powerhouse and big generators, so that I should say flexibility I may lose in the coming years. So for a network operator, it will be quite challenging to manage the whole system, parameters like voltage and the frequency, what today essentially the two parameters which essentially I have emphasized. So yeah, this I will skip. This is the actual general information. And coming to the Indian context, as I told, when this NDA government one came, that 2014, yeah, that time the government of India, that inspired by the international policy, has planned to integrate around 175 gigawatt of renewable power by 2022, and now we are in the 2020, so hardly 2 years left, and we have achieved a remarkable success in that. You can see in the slide bottom I wrote here around 90 gigawatt power is already in Indian context we are generating from the renewable based system, and the majority I should say around 50 gigawatt is coming from the wind based system, and remaining remaining is coming from the solar based system. So wind and the solar will be the potential and the promising resource of the energy generation in the Indian context due to our that geographically locations. The central part of the country has better sunshine. That's why we are going very aggressively towards the PV generation. But as far as the coastal belt of the country is concerned, we have some reasonable wind potential there, and we are trying to tap it. So with this speed, what we are going, definitely we will achieve that 175 gigawatt by end of 2022. And by inspired by this fast progress towards this 2022 this target, government India has revised to go, I think, around 30 to 35% of the renewable power generation by 2030. 30 or 35 somewhere that recently that report came. So what I mean to say, earlier there was some myth whether that renewable has that much potential to cater the energy demand of the mankind in the future year. I think that is no more that doubt is there. So these resources has the sufficient potential to meet the future energy demand, but only thing, since their nature is highly intermediate and highly time variant, so controlling those resources in the network will create some different operational and the technical challenges that we have to look into detail. So this is there, just let us see. Yeah. There's another slide which I kept here. So what is the integration strategy? So this integration, still I should say there is a no clear-cut defined strategy established across the globe, but more or less what I should say, there are some trends. Those trends are same. There is a lot of coherence between the trends what we'll see in the Europe or what we will see in the US and what we're following here in the country. Since their system, especially in the Europe or in the even though US system, the size of those systems are smaller as compared to our system, and our system is quite big and robust in that sense. And their system, as those slide of course I skipped as being a general slides, what we saw in their system already they have a penetration of the renewable around that 30% 40%, and somewhere they have around 100% also. 100% means they are exchanging their renewable power with the neighboring countries, so means their renewable penetration is more than our country. As I told, in our country it is hardly 19 to 20%. So when the penetration level is low of like the 20% or 30%, more or less it is seen that, yeah, it was here. Yeah, more or less it is seen there, they don't create much technical issues. They don't create much technical issues in terms of the voltage control and the frequency control, since still you have around remaining power which is maybe 70% or 80%, because if 20 or 30% is taken by the renewable, remaining still will be from the fossil fuel, this thermal powerhouses, since the still grid will be dominated by the this conventional power plant. So whatever the fluctuations which are coming to the systems from this variancy and the intermittent operation of the renewable, that can simply be offset with the help of the conventional generation in the system. Okay, that is why presently, as our penetration is 20%, we are not facing much technical issue. But there's no doubt in the coming years, like maybe in the next 5 years or the 10 years or the 15 years, so more or less all the grids may have a penetration level of 40% or 50 or 70%. So in that case, definitely our operator has to look for some alternative operating strategy. What he can do. As I told, in some countries already the penetration level is above 50%. So in those countries, what they are doing, since the majority of power generation is coming from the renewable based systems, so in that case, they don't require the power from the fossil fired power plant. So what they are doing, they are ramping down their generations. Their cyclic ramping down of generation is happening to accommodate the this variation what they are getting from the renewable based system. And that is one thing. There's another thing. See, today whatever our system operation works, so that works based upon the 1 day ahead forecasting. Okay, just I will cite an example. Now it's already 12:30. Okay, let us look for 12:30 this power plan in our country for tomorrow. So our that POSCO people, they are working for the power requirement how to meet tomorrow at 12:30 today. So suppose based upon what the information they will get from all the state load dispatch center and the regional load dispatch center, that whole figure is compiled at the national load dispatch center. And let us take an example, that figure comes 180 gigawatt total load requirement at 12:30 tomorrow. Okay, so now as operator, they have to manage that 180 gigawatt generation in the country. otherwise the frequency he can't control, as I told. So there will be open bidding. As you know that there are the power exchange open bidding, and mostly those bids are won by the different, whether it's a central owned generators or state owned generators or the private companies. So they will won the bid according to the least cost. And I will take example of only three players for the sake of simplicity. Player one is the NTPC, and player two is the suppose Uttar Pradesh Power Generating Company, and the player C is some private company. Okay, so as I told, suppose the player A wants the 50%, player B gets the 30% share, and player C gets the 20% share. So since they have to meet a total power of 180 gigawatt for tomorrow, since when the tomorrow will come at 12:30, definitely they will produce the power as per their commitment. There's no doubt. Since those all our power plants are coal fired, they have the sufficient coal reserve. Just they will fire the coal and they will produce the power. If they are the hydro, they have the sufficient potential. They will flow the water and they will produce the power. If it's a nuclear power plant, he is a nuclear that stock, and accordingly he will produce the power. So there's a no doubt. There's a no doubt. Whatever the commitment they have made today, tomorrow they will meet their commitment and they will generate 180 gigawatt. But what will happen at 12:30? So they will generate 180 gigawatt, but the load may be 190 gigawatt. Since it's very difficult to forecast the load, if there's a hardly 5% error in the load, that will make 190 gigawatt roughly. So the 10 gigawatt surplus who will give? If nobody is giving, then it will result in the fall in the frequency. Okay, that is not allowed. So somebody has to compensate for that increased in the load. Since this fall, as I told, these conventional powerhouses are equipped with the governors, so there will be automatic governor action. So accordingly, they will increase their power generation by certain rate. That's the advantage I have with the synchronous machine. Now, question coming. Now I will returning to the point here. What I was trying to make up. Yeah, one more thing. And this, what I told, this economic load dispatch 1 day ahead, it works for the 15 minutes interval. So what the plan which I cited here, that is for 12:30 to 12:45. Since it is assumed that in an interval of 15 minutes, the variation in the load is not so much. There may be some variation. That variation can easily be offset with the help of the primary and the secondary control of the governor. That is there. But when you have more renewable in the system, as I told, if the portion of the renewable is more than 50%, in that case, my dear, it is not only the load side you are getting the error, you will get the error from the generation side itself, because you can't estimate exact amount of the generation at tomorrow 12:30. Since it is not such a stable raw material available to you like the coal or the hydro or the nuclear. So raw material is the wind and the solar. So it is very difficult to predict the amount of that solar insolation tomorrow or the wind speed tomorrow. Though all those three players have won the bid, but they may not able to meet their commitment. So when they are not able to meet their commitment, that will result into the frequency violation and the voltage violations. So it's very difficult. So one option, just I can reduce the economic load dispatch window from 15 minutes to a very small time in which that wind speed or the load variation remains very low. But that will make the grid operation very complicated. So we have to exchange a lot of information within that small time zone. So that is not technically feasible. That is why an optimized time economic load dispatch interval of 5 minutes is advocated across the world. So in the US, they on a I think small system, they are working for a 5 minute window. So it is assumed that in the 5 minute window, the variation, the load as well as the generation can be managed with the help of the ramping the thermal power generation available in the grid. But I don't know, when I don't have any thermal power generation in the system, when totally system will be 100% renewable based, in that case, how those things will be managed, whether it requires further revision in the time window from 5 minutes to 1 minute or whatever. So I don't have much much to say on that, but definitely this attempt will be there to tighten this time window to the lesser, where the variancy coming in the generation, the load will be manageable. So it is there. Uh, Yeah. Now, as I told, more or less, now it is well convinced that so there's no other way to stop the renewable penetration in the grid. Definitely, we have to accommodate that grid. Once we'll accommodate, it will create a lot of technical challenges. So those challenges, just few of them I have listed there. It doesn't mean only there are the 10 challenges. There may be more also, and few I have listed here. Let us try to understand them. First is the variability and the uncertainty. See, as I told, the whatever the variancy we are getting in the input, that is not only daily. So it is varying morning to evening, as well as it has a seasonal variancy. So it is a very difficult to estimate exact amount of the that power generations. So what we'll get. So of course there are different techniques which researcher have developed to go for a better this generation forecasting. What typically what the technique we use for the load forecastings, additional I think forecasting parameters are considered to estimate the generation, but still whether that error what we're getting from those techniques is manageable from the grid operation point of view. So it is still there an open area. So a lot of work is going to, happening in that area. Second is so far as the planning and the operational challenges. My dear friends, typically we plan our grid for n-1 contingency, and fortunately see the whole system is quite stable with the conventional generations. N-1 contingency or n-2 contingency gives us some economically I think feasible as well as the technically reliable result to plan the grid. But once we have the majority of generations in the system from the renewable based system, in that case whether n-1 or n-2 contingency planning will be suffice to manage the grid operation or not, that is still an open ended discussions. Later on I will just export this point when I will go to the asset management. And coming to the another point, that economic load dispatch window, of course, already I have made a one point that we have to reduce the time window from 15 minutes to 5 minutes or low to manage that whole system. So one option is that if I have the better load forecasting as well as the better generation forecasting techniques, in that case, those techniques will be quite helpful to manage the system in a more economical way, and then utilizing the power balance generations to manage the system voltage and the frequency. It is there. And there are some, I think, pilot project based examples where they are managing the system frequency with the help of the balancing the power generation with their neighboring states. But that is only possible where you have that divergent that type of diversity that you have the diverse type of the generations you are getting. If I cite the example of here, I have one state, Tamil Nadu, where they have a reasonable wind potential, but other side, if I say here in the Karnataka, they have the better solar potential. So since both the type of resources may not be at the same times, so I can utilize the support of the one resource to the other neighboring resource whenever it is required. But if I don't have that type of that diversity, so that then it may be difficult to manage with the balance power generation. And coming to the another point, that RE generation, typically dear friends, what is happening in the present regime, as I told, the whole load and the generation is controlled through the load dispatch center or state load dispatch center. And since the frequency requirement are so stringent, but when coming to the renewable, as I told, these resources are not so stable to manage the frequency in a such a that narrow band. So that's why there are the alternate regulations and alternate grid code where they are advocating for a alternate load dispatch centers, are typically also known as the green power corridor, where the frequency control criteria will be different from the renewable based systems. Since there is a no much advantage to driving a system very much in a closed window, so that is why, so they may be looking for the poor frequency regulations essentially from for the wind based systems. Coming to the another point, there's a power system stability. Dear friends, this is one of the main technical concern. So let us try to understand this point in slightly more detail. What happens Suppose you have a very big interconnected system. If there's a sudden loss of generation happening, so that sudden loss of generation will result some stress in the system, or there's a sudden loss of the load. So that sudden loss of the load will generate some stress in the system. And who will take that stress? So just think about it. Ultimately, it is the synchronous machine. Yeah. Yeah, ultimately it is the synchronous machine. Since the synchronous machine has the inherent characteristics of the synchronism, if you give a small stress to the synchronous machine, it will never lose the stability. Like a spring, na? Just you compress the spring, you give some load to the spring, it will retain. If you do too much stretching of it, then it will lose its elasticity. So that type of feature has the synchronous machine. So if you replace that synchronous machine by the PV based system, then since those are mostly static devices, in that case you may not get that type of support what you are getting for a synchronous machine. So the stability will be one of the big concern. Just I will try to explain that stability in terms of the voltage control. Dear friends, typically in the grid, as I told, the voltage is controlled from the synchronous machines. They will always maintain the 1 per unit voltage irrespective of the loading in the grid, since they have the exciter provided to the synchronous machine. So if I have the two area system like area A and the area B, uh, at all the time the voltage is controlled by the machine, as I told you. Suppose in the area 2 you have the PV based system. Okay, in the area 2 you have the PV based system. So what will happen, the PV based system will work in the current control mode. It will follow the voltage of the area 1, since area 1 has the synchronous machine. So the whole system voltage will be controlled by the synchronous machine, and the PV system will follow the synchronous machine voltage. So there's a nothing. So grid, so ultimately what I mean to say, the PV based system is following the grid, and grid voltage is controlled by that synchronous machine. Now suppose in the area 1 you replace that also by a PV based system. So in the both the area 1 and the area 2, you have the PV based system. So since if I take example, the area 1 and area 2 are 100 kilometer away from each other. So at a particular time, suppose at 11 a.m. in the morning, there may be better solar insolation at area A as compared to area B. When the area A has a better solar insolation, you will get a better voltage control in the A as compared to B. So B is following the A. Grid is A is following the grid. But at the other time, at 3:30, the things may go reverse. At area B, you have the better solar insolation as compared to the area A. So at the 3:30, A is following the B, and the B is controlling the system voltage. What I mean to say, it is only two area system I cited. If it's a very multi-area system, there will be continuous hunt for the voltage control in the system. Okay, so it will be very challenging for the operator to manage the voltage system. And there's another issue. This will also give rise to the reactive power management in the system. Dear friends, as I told, synchronous machine has the inherent characteristic to give you the reactive power as well as the active power, but that type of characteristic you don't have in case of this PV based system or wind based system. So they will never give you any reactive power support. So then, since your system is AC in the nature, you have those long transmission lines and you have the transformer in the system, then how you will meet the reactive power requirement in the system? Presently, synchronous machine is meeting the reactive power requirement. So in those systems where you have the only renewable generations, then how you will manage the reactive power in the system? So this is one big concern. But as on today, what we are doing, as suppose I have the 30% renewable and the remaining 70% coming from the fossil. So those thermal powerhouses, they are managing the reactive power. But slowly, as the amount of penetration of the renewable is keep on increasing, and our intention to use the megawatt from the solar power plants, since they are the eco-friendly. But other side, I don't have the reactive megawatt support from these resources. So we are forcing our thermal power plant to generate the reactive power only not the F2. F2 we are taking from the renewable. In the REC2 we were taking from the thermal power plants. But there is no tariff regulations which compensates the thermal power plant for only REC2 power generations. So that is why now I think that grid code revision is going on. The tariff will be also amended so that the thermal power plant will be paid for that type of operation. But that is only feasible we have if we have the sufficient thermal power plant in the future. If we don't have those thermal power plant, once they will retire, since I don't think any this generating company will commission any thermal power plant only for the direct to power generation in the future. So I don't see in that way. So definitely something that alternate solution is required to address this issue for the direct to power management in the system. Then there's another point, the design of the power system protection. Dear friends, what happens whenever there's any fault in the system, you have to clear the fault. Fault can be cleared with the help of the relay, there's no doubt, but those relay only work on the principle of the current and the voltages. Whenever any fault happens, there's a drastic change in the current of the system. Current goes to manifold like that 4 times or 8 times, 6 times, 7 times, depending upon the short circuit strength of the system. And the voltage drops to 50%, 30%, 20%, and even though close to the zero if it's a dead short circuit fault. Since there's a drastic change in the current and the voltage parameter of the system, so I have a very reliable type of the protections based upon the current and the voltage. Distance protection, the current protection is there. So they can detect the fault, they will clear the fault so effectively. So the protection becomes such a that reliable that component of the power system. So we are not facing any problem. But what I told, this whole operation is only possible once there's a drastic change in the current and the voltage. But you just think of a system where you have only the renewable based generations. In that case, if you give any fault, you will not see any much increase in the short circuit current. Since those are the static devices, you don't have the any inertia, so that whose short circuit current is coming from the kinetic energy of this synchronous machine. Since I don't have any now kinetic energy, so in that case I don't get a high short circuit current. So if there's no short circuit current, whatever the protection infrastructure which is given on the system side, it may not able to detect the fault and clear the fault. So this is one of the big challenge in that way. Coming to the wind-based system, what I told, it is relevant to the solar, since solar there's no kinetic energy. Coming to the wind-based system, dear friends, in the wind-based system, of course, they have some kinetic energy. But what happens, what the short circuit pattern that I will get from the wind-based system, it's a totally different what we get from the synchronous machine. Since the size of the synchronous machine is very big, it's a single unit, and typically the short circuit current is very high. In case of the wind farms, so in case of the wind farms, I have hundreds of the machines connected together to make a wind farm, and the spread of the wind farm may be 10 to 15 kilometers sometimes. So at a particular location at A, I am getting the short circuit current depending upon the input level of the wind speed. At other location, I am getting some different short circuit current. So what happens? I have around 100 or 150 or 200 short circuit current clubbed together at the point of common coupling with the grid. So they all are superimposed on each other. When you superimpose the short circuit current coming from the 30 different windmills, you will get a highly, I should say, highly like a noise type of a signal. Okay, highly unsymmetrical, or you say there's no pattern in that short circuit what I get from the synchronous machines. So protections also get in the way the relay get confused to exactly identify whether really it is a fault or it is a just some normal operation of these wind farms due to the variation which is coming from the wind speed. So briefly what I should want to say, what's the protection today we have, of course that is quite reliable, but that its reliability only up to once I have the synchronous machine at source. If I replace the synchronous machine with the PV based systems or the wind based systems, their reliability will be not that what we expect. So we have to look for some alternate or other protection based system. There's another thing, that's asset utilization. So this is also very important point from the power economics point of the view. When we make any new substations, suppose there is some remote area in the Uttar Pradesh, earlier there is some power issue. Now we have identified there is some load requirement and we will plan a new substation to that. Then accordingly, one or two transmission line we have to get from the grid. So ultimately, we are planning a new power that infrastructure in that area with the hope that that resource will be utilized reasonably well in the future, at least for 10 to 15 years. So that is the whole that intention of the planning. But suppose the planning is based upon the renewable based systems, what will happen is the utilization, the asset utilization of that becomes too low. Since the wind, if suppose the plan that holds that power infrastructure substation are the that lines are planned for a wind based system, so availability of the wind is only for few months in the year, so the utilization factor goes extremely low. If the planning is for the solar based system, so out of 365, simply night time you take out, I have only half, and half how much you are getting that good sunshine. So asset utilization is a one of the key issue, especially with the renewable based system. So in order to address that, whether we have to look for some hybridization of these resources together or some alternate option. So this is there. And another technical issue which is of quite prominence, that's the power quality. Dear friends, of course, still today, this power quality is a very grave and very serious issue, but its severity is not that much what we are expecting in the future. So today, majority of the power quality issue we are getting from the power electronics load, what we have in the load area. But so far as the harmonics issue is concerned from the source is a synchronous machine, and we are getting a perfect sinusoidal power from the powerhouse. So whatever the contamination is happening, that happens on the way of the transmission corridors, very less, and the majority it happens on the load side due to the power electronics load. But dear friends, in the future, as I told, when you are replacing that your classical synchronous machine with the help of the PV system, in the PV system, you have the power electronic interface inverters are there, or with the wind based system, you have once again inverters are there. Those inverter will make your signal full rich in the harmonic right at the source. So you will get the harmonics from the source also, and of course load side you have the harmonics. So too much harmonics in the system will decrease the efficiency of the system. So this will be also, I feel, a very quite challenging area in the coming years to how to mitigate and how to localize the harmonics, and otherwise they will travel from generation to the load side. This is there. And there's another point, of course, as if you see the majority of point what I discussed, it ultimately the whole that soul of the all the point is that due to the rich variancy coming from these type of the resources, operator is not able to predict what will happen in the next moment of the time in the grid. So in order to make a better control of the systems, he has to depend upon the decentralized control with the help of the rich communication infrastructure, and that will make the system quite complex to operate. So of course those type of the technologies are available. So but when we deploy that type of technology into the systems, so it will make our this grid mostly a digital type of the grid, and it will create new type of the challenges like to operate, as well as that different threats like we see in the digital world. So those things are there. Slide has stuck, I think. Yeah. So it is, yeah, I have half an hour, so I will manage accordingly. Yes. Now, of course, I told these are the few technical issues. Now, coming to the grid integration issues. When we integrate any renewable resource in the grid, it is not like that some renewable is there just to make a one line and connect with the grid. No, there are the few steps. Typically, those steps are followed. And first, of course, we have to get a very reliable data. Once that reliable data you are getting from that area, then you will assure that what is the exact potential of the renewable. So better exact information of the potential will help you in many ways, will help you for the proper planning, that will you sorry will help you in the proper planning, that will help you in the proper asset management. Okay, later on that will help you for that what I told, that neighboring area control. So keeping this high quality data uh, for wind or solar profiles is a very essential for planning a grid integration into the this planning a renewable integration in the grid. Once we get a very high quality of data, then definitely we will develop the different modules, and where the scenario development type of the contingency studies are carried out. Yeah, then scenario development type of the contingency are carried out. Those contingencies are carried out to define the different options for the future energy fleet, transmission network, and the system operational practices. So based upon that, the feasibility, or I should say the economics of the operations, are decided, and the power system modeling is different studies what are we carried out, and depending upon the weather system stability, or the protection challenges, or the power quality issues, or the planning issues are there, they are explored here. And what I want to say here, when we carry out these type of studies, whether at data collection or the scenario development or this power system modeling, at at each and every state more or less, we have to involve the stakeholder engagement. So it is a very essential. So in this case, who are the stakeholders? It is not the operator, it is not the financer, it is not the, I should say, that owner of any that company, if it's a private company, or if it's a public company, it's not that particular public company. So there are many stakeholders. The first stakeholders, especially for the renewable based system, is the policymaker. So as I told, 2014 onwards, there's a more push towards the renewable integration. Actually, that is driven by the policies. It is not driven by the system requirement. As I told, it will create a lot of issue with the system operation, but the policy is to cut the greenhouse gas emission. So policymaker is one of the key stakeholder in it. So at every stage, we have to involve that by doing this type of operations, or by managing the system in this way. Really, it will achieve the goal what the policymaker has identified against it. So it's a very essential in that way. So second stakeholder in it is the regulator. Essentially, in Indian context, if I say who is a regulator, like CRC and the state electricity regulatory commissions, they are the regulators. So at each and every scenario, we have to ensure the regulator, so it is feasible to operate the system without violating that regulations. If it is not technically feasible to operate the system, then definitely revision in the regulation may also be required, like as cited the example of the frequency control. So regulator is also one of the key holder, and of course then other stakeholders are the financiers, and of course the operator. Operator of course comes at the end. He is to operate the system whatever the case. This I will skip. Yeah, yes, this I will just speak, I think. As I told initially, there were some myths and misconceptions regarding the renewables. One was that the potential need for the increased operating reserve. Since, as I told, their input is highly time variant, definitely we will require some reserve power in the system when I don't have that input, so that I can meet the load. This was the one that myth earlier. When we have the renewable, we always require more that operating reserve. Okay, but how this has been addressed, let us see later. And there is an increased backup capacity. So as if I say the example, if I have the 30% renewable in the system, so does it means that 30% backup power I have required from the alternate resource, because I don't have much reliability on this resource? That is also myth. And then the impact of the variability and the uncertainty on the operating cost increase on the thermal power plant. Since when we are getting a sufficient power from these systems, definitely it will result in the ramping down of the thermal power plant, or too much the variance in the renewable will attract too much ramping of the thermal power plants. So whether the operating cost of that thermal power plant will increase. So let us see what exactly happens, and the technical limits for the VRE integration rates to maintain the grid stability. So earlier, as I told, there was some different opinion that around 30 or 35% we can penetrate the renewable. If we try to penetrate beyond that 30 or 35, it may make the grid operation that unstable. So these were the few things initially when the renewable penetration started, but later the operator have gained the experience from the different operations, and these issues has been resolved in a different way. As I told, whether there's a requirement for more operating reserve, your friend, just see that slide. If I have only 15 turbines, you can see the variation is coming from the 1.6 to 0.6, around 1 normalized output variation. But if you club together all those means more turbine in that area, like the 200 turbine, then the variation in the output power is less. So ultimately, more and more renewable is coming to you, and more diversified type of the renewable based system coming to you, you require lesser operating reserve. It is there. Okay. And then one more thing, if you have the better forecasting techniques, better forecasting technique will result you lesser operating reserve. And of course, there's another thing, and 1 to 2 are ahead. If you are adopting that 1 day ahead technique, what we today already in the practice for the conventional power plant, that will not give you means it will result into higher operating reserve. If you are adopting hardly 1 or 2 hour ahead that forecasting techniques, it will save you at least 20% operating reserve. So it is ultimately what are the different techniques you have to adopt for the different types of the generations which you are getting from the renewables. What are the misconceptions and myths are there? Those are not the cases. Okay, so you don't require the higher operating reserve in that way. And then so far as the ramping issue of the thermal power plants, so too much backup can be used to give a solar variability in a well-planned power system. So how much exactly backup you require? You will require the backup only for that variant portion. If you go to the previous slide, when I have the 200 turbine, the variation you will see from 1.2 to 0.8, only 0.4. So this much backup you will require rather than the full backup. Okay, so you will require only 30% backup. So that backups in present scenario can be given from the thermal powerhouses, because still definitely you may have that much power in the system for the next couple of years. So then coming to the third, in a system without adequate capacity to meet the current or the actually yeah yeah in a system without adequate capacity to meet the current or the growth of the load, yeah, so a mix of the generation can be taken. So this is the example in context to the India, where I don't have the sufficient generation to meet my present or the growing load. In that case, we can go mix with the renewable as well as with the conventional system, but that may not be true in the countries where they don't have the adequate it means where they have the adequate power already available with them. So these are the few things. If a operator takes care of them, so he will be able to operate the grid for the higher penetration of the renewable generation also. Just I will see. Yeah. This is another thing, the impact of the variability and the uncertainty on the operating cost and the pollutants emission from the thermal power plants. Since I made a point there, too much ramping of the thermal power plant may increase its operational cost. Is it true? But there were some that case study has been carried out in the Western United States, where they have reported wind and the solar provides 30% of the system annual demand. Okay, means the 30% total energy demand is coming from the wind in their system, showed a reduction in the projected cost, fuel cost, by approximately 7 billion per year. okay, where the cyclic cost only increased from 35 billion to 157 million per year. Okay, so though there is some increase in the ramping or the cycling cost of the thermal power plant, okay, but that increase is not as much what the saving they are getting from the renewable generations. So overall there is a drastic saving, I should say, and the cycling cost is only hardly 1 to 2% of the overall operational benefits. So now this is more or less clear. Too much ramping of the powerhouses may not increase the operational cost as the what the saving we are getting from the renewable based systems. Since the input is free, the cost of generation from the renewable is cheaper than the this thermal power plants. And that study has also found out that high RE penetration has led around a 29 to 34% reduction in the carbon emission. That was the one of the key requirement of the policymaker. So when you are reducing the greenhouse emission gases by one third at least, so uh, nothing more you want. Ultimately, that was the major aim of it, and overall, there's a saving in the total cost of the system. So these are the few, I think, informations from the European countries, how much penetration they are able to penetrate in the system, and they are not facing much technical issues still. They are able to manage the system. I highlighted few points just to have a glance. The grid reliability is added by the inertia and the primary frequency responses they are utilizing, as I told. So from their thermal powerhouses, solar and the wind typically do not provide these reserve in the conventional manners. So, however, modern wind and some solar plants now have the ability to provide active power control services, including synthetic energy and the primary frequency control. Yes, I will make up this point. So, what happens? Of course, they may not able to provide this type of all responses what we get from the thermal powerhouses. But what happens? We may get a synthetic type of response, synthetic inertial response from these resources. There are the different concepts like virtual inertia, thermal, this virtual inertia, there is a synthetic inertia, where the frequency response can be managed. Ultimately, in the frequency response, what we do, when there's a fall of the generation in the system, the frequency collapse. And it mechanically it will not give you any jerk that absorbing phenomena, but it will help to rise the frequency. How? In conventional system, it is your governor who increases the input and ultimately generation is increased so to make up the that frequency. But in this system, if when you have the sufficient generation or more generation, that time you can store your this power in the battery. When you have that deficit generation in the system, that time you can pump the power from the battery. So in that case, you may get a primary frequency response from getting from the storage devices. So they are using this also we can drop out. Just drop out this point also. Yeah. So I have a very important. I'm getting some little noise. Yeah. Now I have a very important one case study result with me. I wish to share with you people, and of course, those are only confined to India. As I told in 2014, the government of India has devised a plan of 175 gigawatt. Somebody is speaking in between.
Hello, Sonal ma'am, please pick up your mic. Hello, Sonal ma'am, please turn off your mic. Hello, Sonal ma'am, please turn off your mic.
Okay, fine. Thank you. So as I told, in 2014, the government of India has devised a plan of 175 gigawatts of renewable and that integration in the Indian grid. So that time, of course, as a standard practice, so some agency has to carry out that type of study whether our system is able to accommodate that much power without making an adverse effect on the existing without making much adverse effect on the grid operation as well as the existing generation in the system. So NREL US has been hired for this work, and they carried out that one renewable based study for the Indian grid strength for the different scenarios. These were the main objectives of that study. How do wind and the solar contribute to the total generations? Is how much amount will be this, of course. Second, how does net load change? And how do operation of the conventional fleet will change? Conventional fleet means conventional powerhouses in the Indian grid, how their operation will change. How do operation of the hydro will change and whether the hydropower will be affected or not. And then how does renewable energy affect exports with the inter-regional lines? Since this type of resources are the site specific, you may not get everywhere in the country. Suppose if they are getting these resources at in a particular pocket of the country, whether the inter-regional flow lines there, suppose now later on I have the result, of course, whether the import on those lines will be affected or it can be manageable. It should not happen you are getting too much of renewable power in certain pocket of the country and you don't have the much load there, then you have to export whole the power through the inter-regional lines and you don't have those stable inter-regional lines. So this was also one of the aspects. And then what causes RE curtailment? Now this is a new word. Means suppose if they identify through some study 50% renewable penetration Indian grid can handle, really at the all time throughout the year that much power we can take from the renewable, or whether at some grid operation scenario that RE has to be curtailed. That was also one of the requirement. And how does a power system manages forecasting error? These were the few key issues for that study and they have carried out. So one study was carried out with the 100% solar and 60% not sorry 60 gigawatt wind. So through that study they have given the observation it is achievable with a 15-minute overall time scale with the minimum RE curtailment. So they told our existing practice is the 15 minutes with that economic load dispatch window. So with the still same window, the Indian system can handle 100 gigawatt of solar and 60 gigawatt of wind. It doesn't require the requirement for revision to make it 10 or 5 minutes as I was telling. Second scenario, the 160 gigawatt of solar and the wind that time will be around 22% of Indian power demand, providing benefits to the fuel saving and the reduced emission. Okay, and how much is the figure? In the following point you can see. The power system is planned for 2022 is able to manage the added variability of wind and solar. Means the existing power system or what the power system we may have in that by 2022, that system will be able to manage the variancy coming from the wind and the solar. New fast ramping infrastructure such as natural gas turbines is not necessary to maintain system maintain balance in the system. Otherwise, what will happen if you don't have that type of infrastructure? Then you require natural gas turbine. When your solar or wind is going out, that time you can immediately ramp the solar this natural gas turbine. But from that study, it was observed that that is not required at this much amount of penetration. Then, in a system of 160 gigawatt of solar and the wind, coal plants on an average operate at only half their capacity. This is one of the major operations. Once we have that much 160, so our coal plant have to operate only at their 50% capacity, suggesting the potential role of the new tariff structure. As I was telling, because the coal power plants are paid for the active power. But once they are forced to ramp down their generation to 15%, definitely the new tariff structure is required to compensate a plant for their performance. Okay, so it is there. And one more thing, lowering minimum operating cost of the coal plant from 70 to 40% will result around a RE curtailment from 3.5% to 0.76%. If these power plants are forced to operate at 40%, then whatever this 160 gigawatt you have renewable power, you may not have much curtailment. Otherwise, you may have around 3.5% curtailment at certain time. And the final, the coordinating scheduling and the dispatch over a broader area is a large driver. Around 6,300 crore annually will be optimized regionally makes, so that much profit can be attained. So that was a big, I think, that economic this benefit, especially with the penetration of the solars, and without creating much technical issue in the network is feasible for this much penetration. And so far as the carbon emission may fall from 20 to 30%, especially with the carbon emission overall 21% reduction. Coal 20%, gas 20, 32%. So net will be around 21% to 80 million of tons reduction will be there. And further analysis can build upon this basis to explore optimal renewable resources and the infrastructure transmission settings, system stability during contingency, and the influence of the total power system investment cost on the consumer tariff. So this was the general takeaway from that study. And additionally, national and the regional coordination of the scheduling and the dispatch eases renewable energy integration. If there's a national wise that coordination and the scheduling of the renewable power, so it will ease out energy integration and result in the cost saving by the smoothing variability and the broadening the supply of the system flexibility. So means some that opinion was kept where the national and then this regional coordination is required for the scheduling. And the flexibility of the Indian coal fleet is critical to minimizing the curtailment of the energy, renewable energy. This was the one of the another general observation. So since we have good number of these coal-fired power plants, so they will be at the rescue of the renewable curtailment. Otherwise, if we don't have that much resource, then definitely we have to go for the renewable curtailment. That was there. So in this tabular form, so I have compiled, of course, I have taken directly from that report that you can see it. And this was the green power map of the India. You will see majority of that potential is localized on the western and the southern part of the country. And there are around, I think, 3 states where the more than 50% of the renewable power is available. Like Karnataka is there, Rajasthan is there also, and the Andhra Pradesh. Earlier Tamil Nadu was a rich only. Now Tamil Nadu is total is around 40%. And not only thus, that study was not confined to only that 160, 100 solar and the 60 wind. They have carried out a reverse also, like 100 wind and 60 solar. And then they told enables a higher annual RE penetration. If that is adopted, then instead of the 22%, it will be 26%. And reduction in the carbon emission, an additional 6%. Earlier, I think 21%. In that case, additional 6% we can save, and result in the less RE curtailment from 1% to 1%. Earlier it's 1.4% I told. Because of its relative less variable net load profile, the higher penetration is possible, requiring thermal power that plant flexibility. But Government of India has favored that 100% solar rather than the wind, since our solar potential is more stable as compared to the wind due to the placement of our country in the globe. We are in that subtropic region. No? We are in the tropic zone. So that's why it has taken that way. And they have additionally conducted another study with 250 gigawatt of RE. And they what observed? System could achieve India nationally, but around 16% annual RE curtailment in the southern region of the country is required, and some modified strategy for the thermal power plant operations. So in that case, in the southern India, where already this penetration will be quite high, it will result at a certain time on average 16% renewable curtailment. Means we will be not able to harness the total 250 gigawatt. So 16% curtailment we have to do in the southern regions, and moreover, southern regions will require some modified strategy for the thermal power plant. So only ramping down to 40% may not be suffice. So additionally, some more flexible operations were also required. So based upon this presentation, what I spoken in the last 80 minutes, I have compiled few research area for the interest of the young researchers who, if they are there in this meeting. One is the advanced functionality enabled in the VRE to provide all grid services for the stable grid operations. Definitely, we require some more functionality rather than the only few functionality what we have in the synchronous machine. Okay. Then grid codes and the standards are needed to reinforce the grid stability. So some revisions and some more the deeper insight into grid standard and the code is also required for the grid stability point of view. And the need cost effective energy storage methods. Okay, this is one thing where we are looking a future of the power system, especially the battery or any storage devices will definitely help to manage the variability coming from these type of resources. And then improve VRE and the load forecasting techniques. Better the forecasting, lesser the effort with the grid operator, and the source can be managed more better way. And the improved communication from the measurement and the data analytics for better this load forecasting and the generation. Better grid operation and the adaptive algorithms. What the today we have the algorithm, as I told, for interval of 15 minutes. So those we are looking for the better and more adaptive type of the algorithms, which will help us to operate the grid more effectively with such a complex type of generations. And the energy management control for the transmission and the distribution. Presently, mostly we are confined to the transmissions visibility, but the distribution system is nowhere visible. But when these type of generation will be there, they will be in the distribution also. So their visibility is also required. Then the impact of the new load on the system operation and the planning. So it is not only we are trying to see the big change from the generation, a new load like the electric vehicle load, where the portion of that load will be quite big in the future. So nature of that load is quite different as compared to the other loads. So how those load will impact the grid operation, that also need to be investigated in the future. So that's all. Thank you. So I finished as I told. So I kept around 7 to 8 minutes for any queries on this presentation.
Thank you very much, sir, for such a beautiful insight into the current national grid status and its how it operates. So, dear participants, if anyone has queries regarding this presentation, they may ask, sir.
You people can write in the chat box also. I can see it.
Yes, sir. Maybe someone had asked some query in your chat. You can respond to it.
Just I'm seeing. If you can see it, just read out.
No, sir, I'm unable to see it. Actually,
Okay.
there must be some. It would have been given to you only the message.
Yeah, I'm seeing, but there's no query to me.
Okay, sir. No issues then. Thank you, sir. Thank you very much for your valuable time. And
Okay, thank you very much for giving me the opportunity.
most welcome, sir. Thank you.
Yeah.
Hello. So participants, next session will be from 2:30 p.m. It will be taken by Dr. Ruchi Agarwal from NIT Patna. So all of you, please join the meeting at sharp 2:30. Thank you.
This conference will now be recorded.